All right, let's just jump right in. We are living in this incredible moment where artificial intelligence can do things that honestly feel like magic, right? Stuff that was pure science fiction just a few years back. But here's the real question, the one we're going to unpack today. Is any of it actually thinking?
I mean, just stop and think about what these things can do. You can ask a large language model to write you a poem about your breakfast in the style of Shakespeare, and poof, it does it. It can whip up these absolutely stunning photorealistic images from just a few words. And get this, it can even pass the bar exam, one of the toughest professional tests out there. It looks, for all the world, like real intelligence. And yet, here's the twist. If you give that same brilliant-seeming AI a simple logic puzzle, something a kid could figure out, it just falls apart. It fails, and I mean it fails spectacularly. And that gap, that canyon between its amazing fluency and its failure at basic reasoning, that is the absolute key to understanding what AI really is today. So our first step is to peel back this illusion of fluency. See, what we've built aren't these general, all-purpose thinkers. They're more like hyper-specialized savants, masters of one single thing. For instance, you can train an AI to be the best in the world at spotting spam in your text messages. But then, if you show it spam in an email, it has no clue. It's completely lost. You have to retrain it all over again. Why is that? It's because every AI we have today is what we call artificial narrow intelligence, or ANI. And this is so important to get. These systems are defined by their specialization. They are optimized with insane precision for one single task, inside one specific box of data. They're not flexible thinkers, not at all. They are world-class, one-trick ponies. So let's look at the mechanics, because to really get the limits of ANI, you have to pop the hood and see what's going on. And you'll see pretty quickly that it's not magic, it's math. The whole system is basically built on one core idea: interpolation.
Okay, interpolation sounds kinda technical, but it's really just a fancy way of saying you're making educated guesses based on stuff you've already seen. Think of it this way. If you've got a detailed map of New York City, interpolation is the ability to find a new address, as long as it's somewhere inside the city. The AI is an amazing map maker for a territory it knows, but it literally cannot imagine what exists beyond the edge of that map. So when we say an AI understands spam, it's not like it gets the concept of being tricky or deceptive. No, what's really happening is that on its giant high-dimensional map of words, it's learned that the data point for spam is in the same neighborhood as words like winner, click, and free. And it's really far away from the neighborhood where cat lives. It's all just patterns and distance. There's no actual understanding there. So what about creativity? I mean, these things seem creative, right? Well, when we ask an AI to be creative, we're basically just turning a statistical knob called temperature. If you turn the temperature way down, it plays it super safe. It only picks the most obvious, probable next word. That's how you get that perfect but kind of robotic grammar. But if you crank the temperature up, it starts taking more chances, picking less likely words from its map. And we see that as creativity, but what it really is just randomized exploration inside a space it already knows. It's not creating anything new, it's just remixing. Okay, this all leads us to the ultimate benchmark, us. How do humans actually learn? Our intelligence, well, it runs on a totally different operating system. Just think about a little kid learning to walk. They aren't just memorizing a sequence of muscle movements, they're building a deep, abstract model of physics, balance, and their own body. And that brings us to the holy grail, extrapolation. This is the magic. It's the ability to learn a fundamental rule, like gravity, from just a couple of examples, and then apply that abstract rule to a brand new situation you've never, ever seen before. It is, literally, the ability to go beyond the map. And when you put them side by side, the difference is just staggering. AI learns from a giant, static data set, and once it's trained, it's basically frozen. We learn continuously every second of every day. AI predicts within its data. We apply abstract rules to totally new problems. An AI's knowledge is like a flat map of connections, where ours is built up in layers of real concepts. An AI is a snapshot. Our brains are a live stream. This difference leads to an inefficiency that is just mind-boggling. To get fluent, a big AI model needs to chew through about 10 times trillion words of text. A human child? Around 10 million. That is a million times more efficient. Why? Well, because a child has a body. They live in the real world. They talk to people. Their words are grounded in actual physical experience, which is a kind of data an AI floating in a server just can't get. So, all this talk about an extrapolation gap, is there a way we can actually test for it? Like a definitive test? You bet there is. It's a benchmark designed for exactly this purpose, called the Abstraction and Reasoning Corpus, or ARC, AGI.
Now, ARC has nothing to do with writing poetry. It's a series of totally unique visual puzzles. You get shown just 2 or 3 examples of a rule in action, and you have to figure out what that abstract rule is. Maybe it's symmetry, or finding the biggest object, or something like gravity, and then apply it. The key thing is, these rules are so new and weird, they're guaranteed not to be in the training data. You absolutely cannot solve these puzzles by just matching patterns. You have to actually reason. And here it is, the punchline. Humans can look at these novel puzzles and solve them with about 85% accuracy. And the biggest, most powerful, state-of-the-art AI models on the planet, they top out at around 45%. This one chart says it all. It's the massive, undeniable gap between our kind of flexible, abstract reasoning and the AI's brittle, pattern-matching world.
Okay, fine. But what if we just connect the AI directly to a brain? I mean, isn't something like Neuralink the shortcut? Isn't that how we get to real AI by just reading thoughts? Well, not so fast. When you actually look at how these brain-computer interfaces work, you realize they're just another example of incredibly powerful, but still very, very narrow AI.
Let's just walk through it real quick. Step 1, you've got tiny electrodes that pick up all the noisy electrical signals from the brain. Step 2, a little narrow AI algorithm cleans all that noise up and figures out which neuron just fired. And then step 3, a different AI acts as a decoder. It learns to map a very specific pattern of neurons firing to a very specific action, like moving a mouse cursor to the left. See? Each step is its own little specialized job.
And here is the fatal flaw. That decoder is trained on one and only one mental command. Let's say it's the thought of moving your right hand. But what if you suddenly decide you want to control the cursor by thinking about your favorite song? The whole system breaks. It has no idea what you're doing. It cannot extrapolate your intent. It only knows that one specific pattern it was trained on. It isn't reading your mind. It's just recognizing a pre-programmed neural signature.
So, if our current AI is stuck just connecting the dots inside the map, and even hooking it up to a brain doesn't fix the problem, what is the actual path to a true artificial general intelligence? Well, it turns out there are some pretty fundamental walls in our way, walls you can't just climb by adding more computers.
First, there's the data wall. We are literally running out of text on the internet to train these things on. Second, the energy wall. The human brain runs on about 20 watts, less than a light bulb. Training a big AI model can power a small city. And finally, you have Moravec's paradox. This weird fact that AI is great at things we find hard, like advanced math, but terrible at things a toddler can do, like picking up a toy or folding a towel. It kind of makes you think our whole approach might be a little bit backwards.
And all of this brings us to the final and most important idea to take away from all this. The next time you're playing with one of these incredible AIs, just remember what you're looking at. We are not on the verge of creating a mind. We are perfecting the ultimate mirror, a mirror that reflects back to us, with incredible fidelity, all the patterns and knowledge contained in the vast ocean of human data we fed it. It's an amazing tool for exploring the world we've already mapped, but the ability to go beyond that map, to extrapolate, to create something truly new, that, for now, remains uniquely human.